The climate of the Pilbara region is typically arid to semi-arid, and most areas generally have less than 400 millimetres of rain on average per year. The rainfall is highly irregular though, and that's attributed to periodic tropical cyclones which mostly impact the coastal towns. The annual evaporation far exceeds the average annual rainfall, and as a consequence of this dry climate, the vegetation is very sparse. This lack of vegetation also helps contribute to the high rainfall runoff, where there's very little infiltration into the ground, and this results in very damaging flash floods during cyclone events. As discussed earlier, the operating parameters for mine access roads can be considerably different from public unsealed roads. Mine access roads typically have higher traffic volumes, and the size of the heavy vehicles is typically larger than that of public unsealed roads, in that there are quite a high amount of B-doubles, triple road trains and oversized road transporters carrying equipment such as mine haul trucks or modularised ore processing structures. The construction of new public unsealed roads in most cases is unlikely, as the network is already essentially established in Australia. However, the construction of new mine access roads is commonplace, and these are usually carried out in conjunction with and secondary to the development of other adjacent mining infrastructure such as processing plant, railways, roads, etc., and hence why these specifications are adopted. Mine sites also have a very high focus on safety, which we shall discuss in the following sections. Speed limits on mine sites are often below 80 kilometres per hour. Excessive dust is quite a significant concern in the region, and that's exaggerated by the lack of rainfall in the region. Sun glare in combination with dust is also a significant issue, especially with the long working days, meaning that a lot of the driving is done at dusk and at dawn, and this can severely impact the driver visibility. And obviously the frequency of road maintenance and the material properties that make up the unsealed roads are key factors which affect the safe operating conditions. Sealed road specifications are generally unsuitable for unsealed roads. That's because they are usually both too low in plasticity and too low in fines content. Consequently, if sealed road specifications were used on unsealed roads, it's expected that the aggregate fractions would ravel quite quickly. For this study, the material properties requiring specification typically include the maximum particle size, the soil grading, the Atterberg limits in the form of the plasticity index and the linear shrinkage, as well as the bearing strength, which is assessed by the California bearing ratio test. The reason for carrying out these tests is that they are fairly simple and can be carried out on a site-based laboratory and are relatively inexpensive to do. The maximum particle size of a material is significant as it influences the material stiffness, the workability, the riding quality, and the permeability of a material. The maximum particle size will vary for the different layers of an unsealed road, but typically are less than 40 millimeters for wearing coarse layers, but can be coarser for the underlying base course or subgrade layers. For the soil grading, we also need to consider the workability attributes of a material, and we can use the adjacent chart to do so. If the material is too coarse, we effectively have a harsh mixture which is difficult to shape and compact. But if it's too fine, then it's unsuitable, especially for higher traffic loads. The grading coefficient is a concept that was developed in South Africa, and this can be used in conjunction with the shrinkage product, which we'll discuss later, to effectively assess how a material may behave as a unsealed road wearing course layer. It should be noted that because it was developed in South Africa, it uses ASTM test methods which use different sieve sizes to Australian standards, so this needs to be adapted to Australian conditions. The plasticity index is essentially used to assess the behaviour of the fines component of a soil material. The plasticity index method is slightly limited in that it discards materials retained on the 425 micron sieve, and therefore it is not representative of the material behaviour as a whole. Instead, we can use the weighted plasticity index method, where the PI value is multiplied by the amount of material retained on the 425 micron sieve. The following table shows that the WPI value for wearing course and base course layers can be around 400 to 500 for low rainfall areas. As with the WPI, the shrinkage product can be used to assess the linear shrinkage relative to the percent passing the 425 micron sieve. The shrinkage product can be used in conjunction with a grading coefficient to assess the likely performance of a wearing course material, and it can assess for potential defects such as erodibility, development of corrugations or raveling, or slipperiness of a material. As with the grading coefficient, there are differences between the ASTM test method used in South Africa and the Australian standard test method for linear shrinkage. The ASTM bar linear shrinkage method uses mercury, however this practice has been discontinued in Australian labs and several other countries for health reasons. The original author of the wearing course performance chart shown did, however, publish a revised chart for the British standard method for linear shrinkage. This is shown by the red dashed lines. The only major difference here is that the Australian standard and British standard methods use a slightly different size mould. The Australian standard one is slightly longer. So for the interim, the adjustment shown by the red dashed lines has been used, but it's recommended that an Australian standard correlation be developed in future. And the final material property requiring specification that I'll discuss is strength. The SOAK CBR test is a relatively simple test to carry out, and the values for unsealed roads are typically lower than for sealed roads, which use a CBR value of around 80%. By using a lower value, it allows us to make the most of locally available materials. Typically we would use CBR values no greater than 40% for the wearing course materials and no greater than 60% for the base course materials.